instructful to go over this problem right here. The system of differential equations for the current I of t and I2 of t in the electrical network shown is the following. So here they skipped us the step of modeling this ourselves, and they gave us a model for this, and they want us to use variation of parameters to solve for this system given the values for these resistances and these inductances. I hope that's a word. So let's go over to MATLAB and let's see. So the first thing I do is clear all variables with clear all. Then what I'm going to do is I'm going to define the coefficient matrix, and we have A, and substituting the values that they're giving us, we have a negative, open parenthesis, R1 plus R2, where R1 is 8 plus 3, which is R2. And then we have all of that divided by L sub 2, where L sub 2 is 1. Then we can go over to the next entry, and that's R2 over L2, where R2 is 3 and L2 is 1. And we can just not write this 1. And that's the end of the first row. Second row, R2 over L1. R2 is 3 over L1, which is 1, so I'm just going to write 3. And then negative R2 over L1. So negative R2, where R2 is 3 over L1, which is 1. And that's going to be our coefficient matrix. Then we want to define the forcing function. And what is that going to be? I'll call it f of t, and that's going to be equal to E, which is 100 times the sine of t, and we want to define this, and then we want to nope, this is the first row, first column, but it has to be divided by L2, which is 1. So we'll just put that in the first row and 0 in the second row, and we close this. And now we have defined our matrix and our forcing function. So I just have to double check 8 plus 3 here, and it's negative, divided by 1, and 3 divided by 1, 3 divided by 1, and negative 3 divided by 1. And then here we're going to have 100 sine of t divided by 1. So now that we have this, checking the case for A, because we might have one of the three cases, complex, distinct, or repeated. So I'll use the eigen and check for A. Press Control Enter, and it's telling me, hey, I don't know the variable t, so let's declare my variables. And the first one is going to be t. So press Control Enter. We go in over here, and we see that we have two distinct values. So I'll use the Jordan, which is going to output the vectors, and the values. And it's going to be Jordan of A. And I want that to output. From that, what I'm going to do is I'm going to define the complementary solution, because what the Jordan does is it solves the eigenvalue problem. So the complementary solution is going to be a combination of the two solutions that it finds for a 2x2. The linear combination, so I have to multiply by the constant C1, which is a generic constant, multiplied by the vectors. Here this is going to be a matrix, so I'm going to have to tell it I want the first column of that matrix multiplied by the exponent of values, and I want the first column, first row of that matrix times t. And that's going to be our first solution. Then I'm going to have C2 multiplied by this whole command, I'm just going to have to change a couple things. So if I put this over here, what I have is this is going to be the second column because I want the second thing that the Jordan output, the second eigenvector, paired with the second eigenvalues, which is going to be at entry second row, second column. And I'll show you what this does if I press Control Enter. And it's telling me, hey, you need to declare C1 and C2. I always forget. I hope one day I will remember. So once we have those, you're going to see that it defines our solution. See, this is first row, first column. So this is the coefficient of the exponent here, the coefficient of the t in e to the lambda t here. And here we need a 2. The second row, second column. So that's why we put this one. Here we have the first vector, which is the first row, first column of this 2 by 2. So that's how we indicate it. And this second row of this 2 by 2.